Hello everyone, welcome to lecture 17. The title of lecture 17 is Lateral Earth Pressure. So here we're going to talk about what the lateral earth pressures are and how we compute the lateral earth pressures. Actually, the contents of this lecture is similar and has been covered in the Soil Mechanics 2, CE437. So if you're interested in more, there are many examples in the previous Soil Mechanics 2 lecture, so you will find out the useful materials in there. And also the basics are also covered in this handout, so please refer to this handout for more detailed contents and the derivations. Okay. The learning objectives of this class is to understand the lateral earth pressures at rest and under active case and under passive cases. We're going to see what the at rest condition and active condition and the passive conditions. And we'll derive the Rankins lateral earth pressure and compute the horizontal stress and horizontal forces by using this Rankins theory acting on the retaining walls at each case. Each case means that we're going to talk about at rest and at active condition and passive conditions. Okay, let's move on. So retaining structures support the slopes of the Earth's masses. So the main purpose is that to prevent the soil wall collapsing. So you don't want to have the soil wall just collapsing into the highway or into some houses, right? Residential area. So you install some wall to block the soil. So then to design this retaining structure, we need to know the lateral pressure and stress acting on this in this wall. So the objective of this lecture is to calculate what's the force or the stress acting on here. Just note that the pressure and stress will be mixedly used in this lecture. So at rest and active and passive pressures. What is the at rest pressure and what is the active pressures and what is the passive pressures? For example, the at rest condition is that if the wall is static, so there's no movement, so the force is static in the static equilibrium state, so that this wall doesn't move. So then the horizontal stress is applied in this wall, right? And this sigma h is also applied in this soil mass, and sigma h prime is called the lateral earth pressure at rest because the soil is not moving. Then sigma h prime is calculated by multiplication of k naught times sigma naught prime. Here sigma naught prime is the vertical effective stress. So sigma naught prime is the sigma v prime. So that k naught is sigma h prime over sigma naught prime or v prime. Or sigma h prime over sigma v prime. And this is called the coefficient of lateral earth pressure at rest. So here is, so K naught denotes the at rest condition. So that the wall does not move and soil is not moving. So then, what's the case of active case? Active case is when the soil pushes the wall. So which means that if the wall is here, the initial position, because the soil pushes the wall, the pressure is too much so that the wall is deformed to the outward. So if the wall rotates about B to A to B, A prime B, here, from here to here. And then the soil mass will reach to a state of plastic equilibrium and fail sliding down. So as the wall moves to this direction, this kind of the soil mass here will just slide down. So then by during this failure, you can assume some failure surface. And we're gonna talk about the theoretical failure surface angle. And during this active condition, while the soil wall is moving, the wall is moving outward, the horizontal stress is called the active pressure, and sigma A prime, and this is called the active pressure. And again, the sigma H prime horizontal stress over the vertical stress is the some coefficient, and it's called the active earth pressure coefficient, which is K sub A. So we're just talking about the definitions of each case, K0 and Ka for the active case. Then the last is the passive case. And passive case is the case when the wall moves the soil, or wall pushes soil. So initially the wall is here, and because the wall is pushing into the soil, so that the wall deforms to this direction. So then horizontal stress will increase a lot. Right? So then this horizontal stress at passive condition, when the wall is moving into the soil, is called the passive pressure. So sigma P prime. And triangular soil mass here reaches the plastic equilibrium and will fail, and also will, during the failure, it will slide up. Kp, the ratio between the sigma H prime over sigma B prime, or sigma naught prime, is called the passive earth pressure coefficient. So then, if you think about the stress changes with the wall movement, let's say that this is the sigma H prime, the horizontal effective stress, and this is the wall movement, x-axis, or tilt. And say that this is the initial point where you have H prime is sigma naught prime times K naught. So the wall is not moving, it's a steady case. And then if the wall is moving outward, like the active case, so the wall is moving this direction, then horizontal stress here is going to decrease. Right? So it's going to decrease like this, and when the wall is moving into this direction, because it pushes the soil, the horizontal stress will increase. Like this. So then this is the sigma A prime active pressure. So that's sigma naught prime times Ka, and this is sigma P prime, which is passive pressure. So Kp times sigma naught prime. And when you think about the deformation, the amount of deformation required to fail the soil to reach the plastic equilibrium. For the passive case, you require this much. But for the active case, you're going to require this much. So this is delta LA over H, and this is delta LP over H. So in the passive case, it requires a higher amount of displacement. But in active case, very low displacement is required to reach failure. So typical value for the delta LA over H and the delta LP over H. So this is the active case. In active case, in loose sand, you can see 0.001, 0.002. But in the passive case, the 0.01. So it's 10 times larger. Right? Here, it's in dense sand, 0.005 to 0.001. And here, 0.005. Right? So in all cases, right? In clay also, the passive case, it requires a larger deformation or larger displacement of the wall. Then let's look at some empirical relations for K0. So this is the coefficient of the earth's pressure, lateral earth pressure at rest. This is for the case at rest. For coarse grain soil, people use K0 and people compute the K0 from the friction angle, 1 minus sine phi prime, which is called the Jackie's equation. And for compacted dense soil, so there are equation modified from Jackie's equation, 1 minus sine phi prime plus gamma over gamma d minimum minus 1 times 5.5. And for the clay to gravel, Paul Main and Kuhawi also suggested one question based on this Jackie's equation. Is 1 minus sine phi prime times OCR sine phi prime. And this equation also has been used quite a lot. This one and this one. And for OC clay, K0 times the NC, K0 of the NC clay times square root of OCR. This equation is also used. So there are some examples that require to calculate the lateral force P0 per unit length of the wall and determine the location of the resultant force in this configuration. So here you have one soil, but because of the water table, you have a different total density. So above the water table, 17 kilonewton per cubic meter. Below the water table, the saturated unit weight is the 20 kilonewton per cubic meter. So using this, you can calculate the lateral force, the net lateral force acting on this retaining wall. So if you're interested, please have some exercise using this. Okay, next up, we're gonna talk about the ranking theory of the active pressure and passive pressure. So here in this section, we'll see how we can calculate and compute the active pressure based on the ranking theory and the passive pressure based on the ranking theory. Rankine in 1857 investigated the stress condition in the soil at a state of plastic equilibrium. So plastic equilibrium means that the condition where the soil mass on the verge of failure. So it's the time just before the failure. So let's think about the case that this wall here AB is moving to this direction, to the A prime to B prime, and assuming that there's no rotation and only translation, so the wall is moving just horizontally or parallelly, like that. Then we can draw some more circle. So in beginning, you have a more circle here, a small one. So it's inside this more column criteria, so it's safe. But as this wall is moving toward outside, the horizontal stress sigma h prime will decrease. So it decreases gradually. So that here this point is moving toward this direction because the sigma h prime is one of the principal stress. It's a minor principal stress. So the circle gets bigger and bigger, and at some points it will touch the more column criteria. So more column envelope, failure envelope. So that's the point where the failure is expected to take place. So it's gonna occur. So then let's assume that this is the plastic equilibrium that soil is experiencing. Then from some trigonometric relation, we can calculate the sigma h or the sigma 3, the minor principal stress, at this condition. So this here sigma 3 is the same with the horizontal stress. That's the effective stress. See? So if you just understand how this the circle is getting bigger, and when it's tangent to the this more circle, the more column failure envelope, then based on the trigonometric relations, we can calculate the sigma 3. So let's look at this little triangle ACD. Then this is the phi, and sine phi prime. So here this is the effective drained friction angle, phi prime. Then sine phi prime is what? CD over AC. So CD is here and AC is here. So that CD is the radius of this small circle. So sigma naught prime minus sigma A prime over 2. And from origin to center is sigma naught prime plus sigma A prime over 2. And here A to O is C prime times cotangent phi prime, right? So then if you just plug it into this equation, then you have this one, and if you rearrange that, then you can rearrange the equation to express the sigma A prime as a function of sigma naught prime and the phi prime and the C prime. So here active pressure, let me use the pink one, or let me use the green one. Yeah. Active pressure is sigma naught prime, which is the vertical effective stress, times 1 minus sine phi prime over 1 plus sine phi prime, minus 2c prime cosine phi prime over 1 plus sine phi prime. And we know that tangent square 45 minus phi over 2 is the same with 1 minus sine phi over 1 plus sine phi. So this can be replaced with the tangent square 45 minus phi prime over 2, and this one is just tangent 45 minus phi over 2. So then the equation is simplified as follows. So sigma no prime times tangent square 45 minus v over 2 and minus 2c prime tangent 45 minus v over 2. So then if you plot the stress distribution over the depths, for example here, stress, because of this negative term, at the top you have only this term remain because the vertical effective stress is 0, right? Because the depth is 0, so this term will be 0. So that you have negative value of the horizontal stress at the top, and then it will increase as you go deeper with increasing vertical effective stress by this term. So this is the tensile stress region, and this is the compressive stress region. So here the plus is the compression. So as the wall is moving, because the effective stress was so small at the top, you have some negative stress, which is the tensile stress region. And then you have compressive stress region, like this. So we're going to talk about what's the meaning of this tensile strength later in this lecture. The other issue is that, let me see. So from this Mohr circle, we can predict the angle of the failure plane, theoretical failure plane, using some pole method. So where is the pole? Here, still the sigma h prime is the sigma 3, the minor principal stress. So here, and that's applied in the vertical plane. So if you plot the vertical plane here, then the intersection with the circle is here. So this is the pole, so OP. And from here to, if you draw the line, straight line from here to the failure point here, which touches the Coulomb friction envelope, then this is the angle of the failure plane, right? So then you can see that here, this is the major principal stress, major principal plane, and this is the minor principal plane. So that from the major principal plane, you will see you have 45 plus v over 2. The failure plane angle is 45 plus v over 2. So then major principal plane is the horizontal, right? So from the horizontal line, 45 plus v over 2 gives you this kind of angle. And also, because it's a symmetric, you have this 45 plus v over 2 into the other direction. So here, to this direction. So from here, you can see that the theoretical failure plane is about 45 plus v over 2 degree from the major principal plane, which is horizontal plane. Okay. And here, if the C prime, so from this equation for the active pressure, if the C prime is 0, then you can see you have only this term, right? And from the definition of the Ka prime, Ka prime will be 1 minus sine phi prime over 1 plus sine phi prime, or tangent square 45 minus phi over 2. So this is the equation to calculate the active lateral earth pressure coefficient. Okay, then let's move on to the passive pressure. It's the same concept. This case that you have a wall that's moving into the soil. So there's no rotation again. So that as the wall moves into the soil, sigma h prime will increase. So then if the original circle is here, aesthetic case, sigma naught times sigma, k naught times sigma naught prime, then this is going to move to this direction, so that you have circle will be smaller, and then if the sigma h prime exceeds the vertical effective stress, you have this kind of a circle growing and growing more. Right? At some point, it's gonna touch the Coulomb friction envelope like this. So then, now what's the major principal plane or the major principal stress? Sigma h prime is bigger than the vertical effective stress, so that horizontal stress becomes the major principal stress. Right? So this is sigma 1 and this is sigma 3. Right? So then the question is, we have to find out the sigma 1, the major principal stress. So likewise, like we did before for the passive active pressure, we can also derive the sigma p prime using some trigonometric relation, and sigma, which is a sigma naught prime times tangent square 45 plus p over 2 plus 2c times tangent 45 p over 2. And when the c prime is 0, then you have only this term remained, right, from this equation. So then Kp is sigma p prime over sigma naught prime, so tangent square 45 plus v over 2. And so then if you plot this one, if you're looking at the passive pressure distribution over depth, when the depth is 0, you have this positive term, so this much is the 2c pi times tangent 45 plus v over 2, and then it increases as you go deeper. So you have this kind of a stress distribution in the passive case. What about the angle of slip plane or the failure plane? Here, where's the OP, the original plane? Because now the sigma 1 is horizontal stress. Right? From here, if you plot the line, draw the line parallel to the horizontal plane, right? Then it will intersect with the circle here, so that here is the original plane. And from here, you can draw the line to the failure point. And this alpha is what? 45 minus v over 2. Alpha f is. So here 45, alpha f is 45 minus v over 2. And 45 minus v over 2 is from the horizontal plane. So from here, if you draw the line, this will be the potential failure angle of the slip planes. So slip planes is plus minus 45 plus v over 2 for the active case, and in the passive case it's plus minus 45 minus v prime over 2 in the passive case. So this is, sorry, the active case. This is passive case. So the soil inside, in the active case, the soil inside the zone A, B, C prime undergoes the same deformation in the horizontal direction, which is delta LA over L. And here in the passive case, it's gonna be delta LP over L. Then let's go back to the previous pages here. So now that we have, let me see, K naught is 1 minus sine phi prime, and K A is 1 minus sine phi prime over 1 plus sine phi prime, and Kp is, so it's gonna be tangent square 45 minus phi, and this is tangent square 45 plus phi over 2. Okay? Then if we assume phi prime is 30 degree, then K naught is 1 over 2, and Ka is 1 over 3, and Kp is 3. So you can see the magnitude of the lateral earth pressure. So here at rest 1 over 2 times sigma naught prime, right? And here 1 over 3 times sigma naught prime, and here the passive 3 times sigma naught prime. So you can see the relative magnitude among these three conditions. So the last topic, but it's not the least topic, we're going to talk about the tensile cracks due to the active pressure. So we've seen in the Rankine theory, the active pressure is gamma times z, which is the vertical effective stress, times tangent square 45 minus phi over 2, and there's a negative term, minus 2c prime tangent 45 minus phi over 2, right? So, and if we define the Ka as a tangent square 45 minus phi over 2, then you can simplify the equation like this, right? Gamma z times Ka minus 2c prime square root of Ka. For the cohesive soil, if the c prime is 0, then what happens? It's not 0. So when the c prime is not 0, so then you have this negative term, right? So that you have some tensile stress region where the tension is applied for to a certain depth, z naught, and deeper than the z naught, you have a compression or the compressive stress applied at the depth on this wall, right? So then, because of this tension and the soil does not have high tensile strength, actually there's no tensile strength for the soil, so tension crack can occur. So here, up to the depth of z naught, from here to this point, there will be some cracks between the wall and soil, so the wall can separate from the soil, or within the soil mass you may develop some tensile cracks, or tension cracks. So then what's the depth of this tension crack? So the depth of tension crack will be 2c prime over gamma square root of Ka. So where the sigma a prime is 0. So from this equation. So this becomes 0, so that you can find out the z from this equation. And for the undrained condition, if the phi is 0 and c is the same with the undrained strength or the cohesion Cu, then because the K naught, the phi is 0, the friction angle is 0, Ka is, so it becomes 1. So then this equation or this equation becomes just Cu over gamma. So from that, if the soil is cohesive, then you can calculate using this equation, these two equations, you can calculate the depth, the critical depth of the tension crack. And this is important notice that because no contact exists between the soil and the wall up to a depth of z naught, after development of tension crack or tensile cracks, distribution of the sigma naught a, or sigma a prime, the active pressure between z and the h is considered, h z naught, sorry. So which means that if the tension crack is happened here throughout these steps, then from here it becomes 0 and you just consider this much of the stress to the wall, and there's no stress above this depth. Okay, in the class we're gonna practice more, and we're gonna discuss more using some examples. So in the lecture 17, it's a little bit long, but we've seen the lateral pressures at rest and active case and passive case, and we've talked about the Rankin's theory to compute the horizontal stresses.